2007 to 2015. He is also the director of the AI Institute in Dynamic Systems. He received his BS degree in physics and mathematics from the University of Western University in 1994. Subsequently, he was a postdoc in the Applied and Computational Maths program at Princeton, and since then he has been at the University of Washington. So his research interests are wide, so including neuroscience to fluid dynamics, and is particularly interested in integrating machine learning with dynamical systems and control. And during the current academic year, 2023-24, he is going to be a visiting professor at Imperial College London and at the Alan Turing Institute. So thank you, Nathan, for agreeing to give this talk, and you can start now.
Great, thank you very much. Okay, so you guys can see my slides here, correct? And hopefully everybody can hear me just fine.
Yes, sorry, just sorry to interrupt. So just to for the audience, so Nathan has agreed to take questions either during the talk or at the end of the talk. So if you have any questions, please type them in the chat, and we'll get to your question, or you can also raise your hand and we will get to you. Okay. Please carry on.
Awesome, great. And I'm looking at the chat in case anything pops up. So yeah, so thank you first of all for having me here with you guys again today, and hopefully I can you know, kind of interest you in some of this work here. The title, I don't really know what the future governing equations are, but I thought I'd ask this because I think it's certainly with machine learning and AI algorithms, I'm thinking a lot about this, about how we're going to start thinking about the future of science and how we want to start building models from data. And typically we think about governing equations as sort of this dominant paradigm of how we can start constructing models of our physical and engineering systems, and often our physics-based world. And now with sort of some of the advances in machine learning, there's some really interesting options available for us about what we can learn and what we can learn from data and representations of physics and engineering systems. So here's what the talk's really about. It's about thinking about learning from data, a representation, both in terms of a coordinate system, but also a way to express the dynamics in that coordinate system. So I think about these as a pairing. What we want to do is, from the data itself, learn a way to find a model, to learn a coordinate system. So the machine learning tool is going to do that, where we can have some kind of advantageous representation of the dynamics of a system. Mostly I'm going to think about spatial temporal systems or dynamical systems. But in general, these methods can be applied to a broad range of other kind of classes of physics-based models. The important thing here too is we're doing a targeted use of neural net. So we're not just letting the neural net do whatever it wants. We're trying to actually constrain it so that we have some interpretability at the end of the day. So that's something what we want as well in these architectures. So let me be explicit about what I mean. So what I'm showing you here is the night sky. And what you're seeing here in the foreground, that is essentially the trajectories of the planet Mars, and over here is the sort of this is the trajectory of Saturn. And so this retrograde motion, this was physics, right? From the ancient times, before we had writing, people observing the stars and trying to understand and explain the motion of the planets. And so we were trying to come up with constructive theories about how this could work. And the first theoretical construct of this was later called the doctrine of the perfect circle. It came out of 2nd century Alexandria, Egypt. In fact, 150 AD, Claudius Ptolemy came up with this construct of a model. At the center is the Earth, and all the planets you could think about is going around circles and then going around secondary circles. So it was circles on circles. And this was, in fact, sort of this beautiful model that allowed us to make predictions about the trajectory of planetary motion for all the planets that we had observed at that time. And at that time, we knew there were 6 planets, at least when Ptolemy's time came. So this was the first successful theory of planetary motion, this Ptolemaic model. And in fact, it would last for 1,500 years. It was sort of like the Roman Empire of theory, right? There's very few theories in the world that will ever last anywhere close to a millennia and a half, but this is one that lasted that long. And in fact, here you see this beautiful Renaissance painting of sort of this construct of the Earth at the center and the planets revolving around it on these circles on circles. It was such a beautiful paradigm that in fact it almost had to sort of have a religious significance, right? And in fact, when along came Copernicus and Galileo and Kepler in particular, and then when they said, hey, we could change the coordinate system, this was in fact a really big deal. And in fact, it was very threatening to the central dogma as Earth as the center. And this led to, for instance, Galileo being under house arrest. He was in fact forced to recant all of this idea that the planets were going around the sun, this change of coordinate to a heliocentric coordinate system. He had to recant that. He was under house arrest for a long time because the doctrine of the perfect circle was so beautiful that the church adopted it as sort of a representation of the perfection of God. And then when you say it's actually the wrong theory, it created a lot of problems. But Kepler really laid the foundations of the mathematics. He took Tycho Brahe's data, and over 11 years, he had to do this regression by hand to show that, in fact, planets were evolving around ellipses around the sun. So imagine if he had MATLAB or Python, right? He could have probably done this in an afternoon. But it took him 11 years because he's hand doing these regressions of all this planetary data to find, in fact, this theory about planetary motion, which we call now Kepler's laws. Now, the important thing that happened there was once we had the right coordinate system, now we could posit what Newton did is came along and posited F equals ma, right? So then he came up with this calculus, he developed a new theory, and he explained the force, this gravitational law, this inverse square law, and wrote down F equals ma. And you had to have the right coordinate system in order for this to happen, right? So once you get the right coordinate system, you can have your F equals ma and this beautiful representation of Newtonian physics, which actually completely changed the way we did all of physics, all of mathematics there going forward. And this isn't the end of it, though, by the way. After Newton, it's another 187 years before we get better and better observations of the night sky. And we realize, wait a minute, something's not quite right. This Newtonian math does not explain planetary motion. And in fact, this is what led directly to Einstein's theory of general relativity, where he basically building upon Newton's ideas said, well, actually, gravity warps time and space locally for very massive gravitational objects. And so we have the origins of gravitational general relativity. So this procedure basically going, you could see the timelines here, right? So the Ptolemaic model is just simply geometry. And in fact, it was just circles. So, and Euclid had laid down the foundations of geometry. In fact, he summarized them in his Elements in 300 BC. This is almost half a millennia before Ptolemy was able to just write down a simple model with circles. It would take another 1,500 years for Kepler to really lay down Kepler's laws and really formally establish this new coordinate system, which is the heliocentric coordinate system. And it took 87 years after that to have F equals ma. And then all the way in 1915, we have relativity. What's so exciting about right now in history is the James Webb telescope is in the sky, and this is a new data collection method, right? You can think of it as a new sensor, and I think it's going to revolutionize the next step in our understanding of the universe. So every time we collect better data, we can build better models. But instead of waiting thousands of years, what we're hoping to do with machine learning is massively accelerate this process by using the tools that we have available to us with machine learning. So let's talk about the models, because it really frames what we want to do in this talk, which is the first model is this one here. So if we go back to my structure I wrote down, which is a encoder-decoder neural network with a latent space, I'm going to feed in, you know, basically a video of my night sky as the planets move. And what I want it to do, I want this autoencoder to learn a very advantageous representation. And one advantageous representation to learn is the Ptolemaic model, which is all I need to do is learn circles on circles. So in other words, learn the radius of a circle and the angular velocity. One way to think about this is the earliest Fourier transform we have, right? This is a Fourier transform in sort of a really beautiful representation of this. And the decoder brings us back to the original coordinate system. So that's model one. It's perfectly valid model, right, as an approximation to the planetary motion. Model two is the one we think of as the correct model, but it's still this kind of idea. You feed the data in, you want it to learn, go to a new latent variable, and what you want this thing to do now is learn this coordinate system, which is the elliptic orbits that go around the sun, not things going around the Earth, and then learn this inverse square law and F equals ma. So these are two different models, both of which can give you an accurate representation of planetary motion. In fact, either one is just as accurate as the other if you want to use either model. So which is the right model? Obviously, we typically teach this in school, right? This one right here, that the sun is at the center of our solar system. But the fact is, as a representation, both are valid in terms of making approximations. So I want to kind of dig down on this, because these two models that we can think of, you know, we think about what Kepler did in terms of establishing the coordinate system and Kepler's laws, and we think about Newton's F equals ma. We could always ask, okay, so what's really the difference behind, you know, Kepler to Newton? Because one of the things that's interesting is we always think as Newton is the more transformative of the scientists, right? And Newton is the more famous physicist, the more had the biggest impact. But really, if you solve F equals ma for planetary motion, what the solution is Kepler's ellipses. So why is Kepler not more famous for this? So here's the point I want to make here is Kepler, what he actually did ultimately is an interpolation on the data. He built a model to fit the data. What Newton has with F equals ma is something much more astounding. He not only can fit the data, but then you could do the following thing. You could say, I wonder what it'd be like to launch a rocket from the Earth, put it in orbit around the moon, and bring it back. This is something that Kepler does not have data for. Kepler can only model what he has data for. What F equals ma and what governing equations are is it gives us the possibility of extrapolating into regimes where we have no data whatsoever. So that's the power of governing equations. And in fact, our first moon missions and our first moon launches were all based upon models that we built, physics models, because we certainly had no data before we landed on the moon. But we believed in the physics models, and that's how we got our vehicles there and back. How does this play out today? Well, here are two of the, you know, this is our generational problem right here. This is the state of the art, robots, self-driving cars. And they're both autonomous vehicles, right? They both have powered by AI learning agents, but there's a really big difference between them. The robot as an autonomous agent is actually built around physics-based models. And so, because in some sense, the robot has to stabilize itself and extrapolate its physics in order to do this. The car is built upon no physics, essentially. It's built upon a bunch of sensor banks, LiDAR, vision, cameras, and with that, it learns a bunch of rules to drive on the road. So another way to say this is, It's very much like this. This is a physics-based model. This is a no physics-based. This is purely an interpolation engine, where it's at least trying to be an extrapolation engine. So the top one sort of inherits the legacy of Newton, while the bottom one inherits more of the legacy of Kepler. Fit the data to the best model possible, right? And you hope to collect enough data that the world you live in is an interpolation. By the way, it's interesting because if you start looking at some of these robots built on these models, you start to see them, they can certainly fail just like humans would. Check that, if you look at this, these things are not perfect. They make mistakes. They make mistakes in their state estimation. So it's going to be very interesting to see these autonomous vehicles interacting with us in the future, because like we fail, these things seem to also fail in many interesting ways like we would as humans. So anyway, we still got a long way to go to make them perfect. And it's not even clear we can, right? So perturbations can destabilize these. And so we're going to have some mistakes just like humans have mistakes. But by the way, we're not tolerant to mistakes from machines, right? Like if your friend makes a mistake, you might be mad at them and they apologize and you get past it. But like when it's a robot that makes a mistake, there is no forgiveness. It's like you gotta okay, take all the robots away. They failed. So it's going to be very interesting to see how we handle this, because clearly robots and cars will fail once in a while, and we're going to have to figure out how much risk tolerance we're going to accept from those. Okay, so that's laying the background for kind of many things we want to do. And the Newton-Kepler story really laid down the foundations of what we want to go after here, which is what we want to do is we're going to start off with data that we collect from sensors. And this, I may or may not even know, kind of in some sense, the right variables for the system I'm measuring. All I know is that some sensors on that system pulling information. That's the Y here, measured at different time points. And what I want to do from that is learn a mapping from Y through some measurement model to the state space. So I'd like to actually learn the right coordinate system. So X you can think of as the right variables for that system. So I would have to learn what H is, which is how to map what I've measured to X, which is somehow the right coordinate. So I have to learn H and X. And then I want to learn sort of the governing set of equations for X. So what is X? So F is what's specifying what the dynamics are. So I have to learn F and H and X. This is a terribly ill-posed problem. So normally when you talk about this problem, when I was in grad school, when we hit an ill-posed problem, you just said, okay, that's ill-posed, let's go do something else. But now I've learned in doing machine learning, if it's ill-posed, you say, okay, that's not a problem. All I have to do is impose some kind of regularizations or constraints on the problem to make it well-posed. And so that's how we're going to solve this. And you can ask the questions, what do I want to impose on this to make it well-posed? Well, here's kind of where we're going to go with this. We're going to use physics-based ideas. What we want is ideas of interpretability and parsimony. If you look at, in my office right above me are all my textbooks, and we have all these governing equations in physics, and it's remarkable, like, quantum mechanics, the Schrodinger equation has 3 terms. Maxwell's equations, if we look at the wave propagation, it's 3 terms. I mean, it's remarkable that you can represent very complex phenomena with very few terms. And so that's what parsimony is going to go after. We're going to try to build models that don't need very many terms to represent very complex things. And these ideas go back a long way, all the way to the time of William of Ockham, from which we derive the term Occam's razor, in which the idea is to use as simple a model as possible that gives you a fairly good model, but use nothing more complicated than you need. And William of Ockham was actually, where he came from this idea is that during his time at Oxford in the 1200s, when they were starting to pick up again on Aristotelian logic, they were building these very grand constructs of logic, and William of Ockham was saying, look, no, make it as nominal as possible to represent the concepts you need. And these ideas pervade throughout history. Pareto I put up here because we often talk about what's called the Pareto front or the Pareto frontier of models, which is You want the simplest model possible that gives you an accurate result. That's sort of the right model in some sense. So for us, the ultimate physics regularization of what I'm going to try to do is I want the smallest number of terms in the smallest number of dimensions. And in some sense, that's kind of how we've built most of our physics models. We try to find the right coordinate system. In other words, somewhere where the physics is very nice and compact, and in which I can write down the physics model for the dynamics very nicely. So that's what we're going to go after. That is our regularization for that equation. So that's what we're going to do. That's how we're going to solve this ill-posed problem. But there are some issues that we have to address immediately. And this comes to the fact of why I showed you the Ptolemaic model versus, right, the Newtonian model of, celestial mechanics. So I want to give you a governing partial differential equation here. This is the Burger's equation. It's the simplest nonlinear PDE you typically encounter. It's like the first one I saw in grad school, right? Here's a nonlinear PDE. What do you do with a nonlinear PDE? You can't solve it typically explicitly, so how do you deal with it? And this is Burger's. It creates shocks, and these shocks are regularized by diffusion, and let's call this our truth model. Well, in the 1950s, when they were studying shock waves, Cole and Hoff actually discovered this very interesting transformation. They did it independently at the same time, which is I could work with this nonlinear PDE, U, and you don't even have to care about the nonlinear PDE. All I'm going to tell you here is that, hey, there's a transformation to a new variable V, and in new variable V, that nonlinear PDE becomes linear. Now that's fantastic, right? Because all of a sudden, something I couldn't solve with pen and paper, I get it to the heat equation, which I can write down a solution for almost immediately. In fact, there's a possible solution to this there, where maybe I have it's on a domain 0 to L with, with zero boundary conditions, for instance. And so there, I can just write down the solution. And of course, I would never sum this to infinity, right? You just go to some large n. So maybe what I'm trying to tell you here, in fact, and by the way, here's the numerical solution. Everything you're looking at here on this page, the nonlinear PDE, a linear PDE in a different coordinate system, the solution, or this, they're all manifestations of the same physics. Now, here's what's interesting about this. I, as a machine learning person, can decide what do I want my machine learning agent to learn. So in other words, I could take data and try to say, could I learn this PDE? But wait a minute, if I learn that PDE, what I'd really like to do is find a solution to it. So maybe I should just have learned this PDE instead. Why would I learn this when I could maybe learn in a new coordinate system this linear equation? But why would I learn the linear equation maybe when I could just learn the solution directly? You see, there's a lot of choices you can make here. So you can even learn a discretization of the equation if you'd like. So anyway, this is the big question. And this is why I asked this question about what is the future of governing equations, because even though typically what we do as mathematicians, we start off with like, here's the governing equation, let me go analyze it. You have the potential with machine learning to take data and say, well, I could have my data try to learn the governing equations, or I could have my data learn directly for me a coordinate system where the dynamics is linear. You see, there's a big difference between those. And so, and part of it is just for you as a researcher to decide what do you want your machine learning to go after. And we'll talk about this. So another way to think about this, these are all manifestations of the same thing. And I like to think about it from a biological perspective. The governing equations are like DNA. From DNA, it sort of is the encoding of the essence of what a human being is. If you grow this strand of DNA about 30 years, you get an individual over here, a person. So a person grows under different, we call it nature and nurture. In other words, in the math terms, this would be initial conditions and boundary conditions. And so if you do a specific simulation, you get a specific outcome. And it's the same with DNA. You grow DNA under nature, environment, and the genes that are inherited, and you grow a different person. And these are just different representations of the same thing. So for you as a scientist or as a mathematician, you get to pick what you want as your representation. So that's the idea here. This is not as simple as I made it sound, like, oh, we're just going to go learn a model. It is up to you now to figure out what do you want to enforce on this in this learning process, because you have some choices that you can make here to learn things. So let's go learn some things. The easiest thing to do is to do something very much like what Ptolemy did, which is to say, how about this? Since I've already shown you that, for instance, even in the Burger's equation, there's a transformation to a linear model. Why don't I just try to directly learn a coordinate system where the dynamics are linear? So if I come back to here, I just want to learn a representation x, a coordinate, and a measurement model h, so that the dynamics f here is linear. So find a way to embed exactly this in a linear model. Okay. So linear models. Why do I love linear models? And why do you love linear models? It's the only one these are the only ones I know how to actually solve. I can only write down solutions to this, right? So here it is. Here's a linear model. The x to t equals ax. You do an eigendecomposition, there's your solution. Okay, so I always tell my students, part of your job as a grad student is to convince yourself you can do fancy things, but don't forget that the only thing you really know how to solve is a linear model. So there's a linear model. And so I want to train this to do this, because if I can get a linear model, I can write down solutions. So let's talk about how to build a linear model. Well, the easiest thing to do with a linear model is to actually regress to a linear model on the data. And so one of the ways to do that is through what's called the dynamic mode decomposition. So here is my student Dia and my former postdoc Travis, and we did this what's called optimized dynamic mode decomposition, which is I measure a system and I take snapshots, spatial temporal snapshots. So each column is different time. And this is some high dimensional system. X is the state space, and it can be n dimensional. And so what I'm going to do with this data snapshots is I'm going to basically say, hey, how about if I fit a linear model to this? In other words, what does that mean? It means a linear solution. I just showed you it had some amplitude, some mode, an exponential part, and some loading. So here's the mode, the eigenvector, the eigenvalue. I'm just going to directly regress to a linear model from this. And to make this more stable, what we're going to do is do what's called bagging optimized DMD, which is we're going to take subsamples of this, because if we have noisy data, we don't want to be thrown off by the noise. So I will take what are called bags. I'll take random subselections of the data, fit a model, do it again and again and again, so that when I get this linear model out, I have the mean and the variance of these modes and their frequencies. And so this allows me a very, very simple representation. We're not really doing machine learning here. We're just fitting linear models. And this is one way to get yourself a very fast linear model out of the system with almost no work. And in fact, you can just keep building linear models as your time progresses. So you just have a local linear model. It's sort of a generalization of doing a Taylor series expansion on spatial temporal data. So it's very fast, easy, and accurate for a certain amount of time. But if we want to do something fancier, then we bring out things like neural networks. And so what you're looking at here is this is work with Bethany Lush. So she was a student and then later a postdoc with us. And so what she said is, how about this then? You want to learn something like what we saw before, which was I want to learn a transformation into a linear model like we did for the Burger's equation, the Kohl-Hoff. So how about if I take the input, I learn a mapping to a latent space, and what do you want to have happen in a latent space? Well, once you're in the latent space, when you go from y of k to y of k plus 1, in other words, you take one step into the future, you want that to be a linear map. And if you take two steps into the future, it's just that linear map squared. So in other words, in this latent space, I want the dynamics to be progressing according to a linear dynamics, and that's what you're going to enforce. And more than that, you see something interesting here. Notice that you have a choice to make here. And I'm not saying this is wrong or right, but if you want to make this always work, you just make your neural net go to infinity. If you want it to be linear, you just go to infinity, it works great. That's not what I want. I want, remember, parsimony, lowest number of dimensions, lowest number of model. So I know that if I, for instance, here am going to encode something like the pendulum, a fully nonlinear pendulum in a linear model, I know the pendulum has 2 degrees of freedom. So I want this to be 2 degrees of freedom. It's consistent with physics. So I'm going to constrain it to be at the dimension of the physics itself. And that's where it makes it challenging. So when we do this, what we have to do is we have to actually parameterize this linear model by the frequency of the oscillations of the pendulum, for instance. And that's what this does. So there's a network. This is a hyper network, because this network tunes this network. So this is a simple 2 by 2 linear matrix, which is parameterized by the frequency of oscillations. And when you do this, you parameterize the continuous spectrum, essentially, which is common in a lot of our models. So you can take this pendulum and you can embed it all the way up to the saddle point at the top, this fully nonlinear pendulum, which you can start seeing here as you get large oscillations. It's pretty nonlinear. You can embed it all into a linear model. So this shows you that essentially this is equivalent to sort of like the Kohl-Hopf transform for the pendulum. I take the nonlinear pendulum, I found a transformation to make it linear. Let's take something more complicated. Flow around the cylinder. I take flow around the cylinder, I take this full spatial temporal PDE, I look at the low dimensional embedding of it, which is some nonlinear dynamics, which is actually very low rank, 3-dimensional, but nonlinear. I can then warp that through this neural network transformation into a linear model. So this flow around the cylinder where this von Karman vortex shedding is happening, I can build a coordinate system where all that dynamics is linear. So these are the kind of things you can do. And then we continued this idea with Craig Jin, who you're seeing here. And what Craig did is something very interesting that was, I thought, pretty remarkable. So what Craig did, he said, okay, how about this? I'm going to take something like the Kuramoto-Shibashinsky PDE. It's full spatial temporal chaos. So, it's a canonical model we study for when we're going to talk about chaotic spatial temporal systems. So we run this one. And what surprised us is that we thought we would never be able to do this, but Craig did it. He actually took lots of different trials and training data, and we learned a neural network mapping to a latent space where the dynamics of the chaos equation are linear, or approximately linear, I should say. They're probably not exactly linear. Certainly there's some issues there, but they're really a very nice representation. So what you're looking at, these panels on the right, is the exact numerical solutions, and this is our model evolving under a linear equation and then decoding it back to the original variable system. And it works amazingly well. So basically what Craig found is a way to, it's like something like the inverse scattering transform for something like the Kuramoto-Shibashinsky model, which is really quite surprising. So anyway, this one here I think is really fun because it suggests to me and to us maybe as mathematicians that there is hope for us to actually embed in linear spaces much more complex PDEs than we thought possible, because the computer can do it. And if the computer can do it and the neural network can do it, maybe we could do it too. Okay. And you can also do this for Green's functions. So this is Dan Shea, where we actually said, okay, let's try this for boundary value problems. And we were able to actually take a nonlinear boundary value problem, learn a transformation to a new coordinate system where it's a linear boundary value problem, which means we could use all the power of a Green's function solution, our fundamental solution in this new coordinate system. So all those ideas carried forward. We can also take this idea of warping coordinates and then warp time directly. So you can say like, okay, so we warped space. How about I warp time? So think about this. This is work by Henning Lange. I have some time series data. Here it is. It can be quasiperiodic. But even here, this time series data, you see it's very spiky. So if you were to look at this and do a Fourier transform, because of the spiky nature of the data, it would cost you a great number of Fourier modes to represent it. But it's a very simple looking spike, right? It looks fairly periodic. What if instead we were to warp this through a neural network? So in other words, do a representation is very closely related to Koopman theory, which is learn a neural network transformation that tries to warp the time series into as few sines and cosines as possible as a representation. So all we're doing is stretching and pulling time in the right way so that I can use as few Fourier modes as possible to represent this. And in fact, that's exactly what Henning was able to do, is learn that warping of time and space. And by the way, this is no different than what Einstein did for general relativity. He basically saw that gravity was warping time and space. We're doing the same thing here, except we're letting the machine learning tool learn the mapping of what it has to do to time to warp it to make things as sinusoidal as possible. And so I want to show this chart because I love it, because oftentimes you'll read in literature, oh, if you want the best time sequence, you just go to an LSTM. You know, now it's more transformer networks, but okay, LSTM, there it is. And I just want to show you this Koopman model. The error just crushes all these leading LSTM, Drew's echo state networks, ARIMA models. So classic statistical models, the leading machine learning models, and this sort of more physics-based modeling approach just destroys them, does a much better job. And so now you can start building reduced order models from this. So what you're looking at here is this is the dynamics of this cavity-driven flow. We can look at a low-dimensional embedding. The data looks pretty quasi-periodic, but we learn a warping, and then it's simply trivial to represent this. And in fact, we can forecast this way out to the future in a stable by construction, whereas you try to do projective reduced order modeling, you get an unstable model for this that you still have to run ODE simulations for that are costly, whereas this is just dirt. You have the solution for any time in the future you want. So this is a nice, very nice representation, and it's built on the same ideas we have here. Just warp time or warp space to build a linear model. Okay. So that was step one, right? Like the easiest thing for us to do. And I always like to start easy because that's if you can do it, you should always just do the easiest thing, right? Is we took data from some nonlinear dynamical system, and we found a transformation to try to take that data and build to make it as linear as possible. And that was my constraint there. I imposed that constraint in my regularization for solving that problem. Now we're going to say, well, okay, I'm going to let my model be nonlinear. What can I do with that? So this is where we introduce a different method called the sparse identification nonlinear dynamics, or SINDy, we call it. And what SINDy is basically AX equal to B. So I want everybody to understand all I'm going to do is solve AX equal to B here. There's no hard math in this, right? What it is, I'll tell you what A is, I'll tell you what X is, and I'll tell you what B is. So I'm going to give you some time series data. And I'm going to tell you that time series data came from some governing dynamical system. Some x dot equals f of x. But I don't know what f of x is. But I give you x. I measured it. Well, from x, you can produce x dot. So you have x dot equals f of x. You don't know what f of x is, but I can generate an approximation of x dot, right? I just numerically differentiate my data. So that's b in ax equal to b. What's A? Well, A, it's here it's called theta. The A is going to be basically a library of potential physics models. So x dot equals f of x. What is f of x? Well, everybody is in this call is overeducated and has way too much knowledge about models, and you have probably textbooks somewhere with all kinds of physics models. And you could say, hey, I've learned a bunch of models. Your library here is made up of these models you've seen. Polynomials, quadratics, cubics, quintics, maybe some sines and cosines, whatever you saw in your differential equations courses, you can put it. Each column is a candidate for the right-hand side f of x. And you make a big library of them. You say, here's all the things I've seen. And what you know is, from parsimony, is that anytime I've seen governing equations, usually it's 2 or 3 terms. So we're going to say is out of this library, probably I only need a few terms to model my system. So x dot equals f of x probably only has 2 or 3 terms. So what I'm going to do is solve ax equal to b, and I want my solution, which is here, big C, which are the loadings or the coefficients in front of these library terms, I want almost all of them to be 0, except as few as possible. So we promote sparsity in that AX equal to B. And what this does here in this system is I give you the time series data, you produce the derivatives, and now you regress onto a library of terms. And these dots here tell you the terms that are non-zero. And what are these terms? They're Lorentz terms that actually produce the data. So it's a way of recovering or inferring the dynamical system that produced the data that can be nonlinear now. So for instance, we did this here with Sam Rudy, and we recovered a bunch of PDEs that are pretty common to learn in grad school, right? These are all these nonlinear PDEs. What you get is just the data. Here's the data on the left. I give you spatial temporal data, and I ask you, can you tell me what PDE produced the data? And so this regression architecture takes that data, regresses on a library of potential terms, and what it finds is it actually recovers your governing PDE. Covers the KDD, Berger, Schrodinger, nonlinear Schrodinger, KS, reaction diffusion, Navier-Stokes. And so this is a really nice, fantastic framework. When we first did this, we couldn't tolerate very much noise, but now in this package, SINDy, we're on 2.0. We have a lot of new innovations that really help stabilize learning these models, even under fairly large noise considerations. So if you want to play with it, it's as easy as, if you got your Python open and you're listening to my talk, you could do it in real time. You can say pip install SINDy. Boom, you got the package. And there's all kinds of examples in there you can walk through and learn how to use it. So we try to make it very, very easy to use for that. And so this is a different way. Notice that we learn nonlinear models that are parsimonious and interpretable. Okay. Now, one thing I swept under the rug in that last piece was I assumed I already knew the right measurement coordinates, right? When I gave you this, I said, oh, look, I measured this. I was already measuring the right variable. So the question is, yeah, but at the beginning I said, what if I don't know the right variable? So part of what I want to do is I want to start thinking about what is the right variable. And how do I learn the right variable? So now I want to do what I actually professed at the beginning and what we had to do in two pieces. So first we had the Ptolemaic model, and it took a long time for Copernicus and Kepler to switch the coordinates, another 87 years for Newton to get the governing equations. We want to do this jointly. We want to do it all at once. So we want to discover a set of coordinates where the dynamics has some very nice representation. So how do we do this? So now we come here, and this is work with Kathleen Champion. And so Kathleen did this work, and this is one that I'm really kind of happy with, because we're still trying to make this more robust and stable. In fairness, we can't. This one takes a bit of hyperparameter tuning. You have to have pretty clean data, but we're working on trying to really, just like we did with the SINDy model, we've really taken big steps over the last 6 or 7 years to make it much more robust to noise. Here, the architecture and the idea I think you'll appreciate, which is I'm going to take measurement data. And now what I want it to do is I want it to find the right coordinate system here. And what do I want to have happen? What do I mean by the right coordinate system? In the right coordinate system, I want to impose SINDy. I want there to be a parsimonious representation. In other words, I'm going to measure a system now, and I don't know what the right variables are, but I want this autoencoder to find me the right variables where when I represent the dynamics in these variables, it's parsimonious representation. So this brings in all the ideas of dimensionality reduction, right? Find the right coordinate embedding. And it also brings in a lot of our traditional physics thinking of governing equations somehow are the right representation of physical models, because you can capture bifurcations, instabilities. This is how we've built most of our technologies, by having really good governing equations. In fact, you see my iPhone. My iPhone here was built by having governing equations, Maxwell's equations, Schrodinger's, so quantum and E and M. And from it, we built models, we extrapolated, then we built some experiments to verify it, built new models, extrapolated, and eventually after decades and decades, you get something to an iPhone, right? And it'll be fun to see what we get next in our technology world. But this is what this is trying to do, is kind of set up an architecture that automates this. And by the way, there's the entire loss function. So we have a standard reconstruction loss associated with an autoencoder. So go into this variable, come back out, you should be able to reconstruct what you started with. And then you impose this SINDy loss, which is just a sparse regression, both in the latent variable and what the latent looks like in terms of the original variables through the autoencoder, and then promotes sparsity on the library term. And then that's it. Okay? And so what this does, and let me just show you the example, because I think this example is, I think, really key for us, at least in terms of thinking of how we want to think future-wise. So what you're seeing here is a video of some pendulum, right? So I show you two examples of the pendulum, and we're going to train this with data like this. So you see, this is actually an experiment right here at the University of Washington. We just drilled a hole in the wall, put pendulum in there, and videotaped it. So the data coming in here is pixel space. It's video. So what's coming in here, this architecture has no idea that this is a pendulum. It has no idea what theta or theta dot are, or that those are even variables. All it has is changing intensities of pixels, which make up the video. Okay? So what has to happen? Well, what has to happen, it has to take in this video, and what I'm going to force it to do is say, you have to find me some variables where you can represent the dynamics parsimoniously. So what it does, it says, okay, so you feed me all these videos, I'm going to learn this variable. In fact, it does. It learns theta. We give it no information that theta exists. It doesn't call it theta, right? I mean, it just gives you two latent variables out of the system, one of them which is theta, the other which is theta dot. And once you have these, and the reason it learned those is because you were forcing a parsimonious model, and this is what it learns. Right? So this is the power of what a neural net with enough data and enough regularization can do. What you've actually told it to do is said, look, I want you to go find some parsimonious. It has to learn theta because this is the most parsimonious representation of the dynamics possible. And by enforcing that parsimony, it learns the entire pipeline for us. Another way to think about it is, if I gave it pictures of the stars, a nice time course of the stars, it could then extrapolate from the night sky and the motion of the planets. It would infer that everything, it would infer the heliocentric coordinate system and then infer F equals ma in the inverse square law. Now, it turns out getting that data into there is a little tougher than you think, because we try to do this with Tycho Brahe's data, or which Kepler used. But it turns out Tycho, he would keep going down to the court in Copenhagen. And so you get these small patches of observations when the night sky was visible, and then all of a sudden he'd take off for a few months, and he'd come back, and maybe 6 months later. So it was very intermittent data. And so we plus we'd have to hand transcribe this, because it's all in a PDF file that we have, but we'd need to turn it into real data, which you haven't done yet. So anyway, but that's the idea of what we have here. So this is this brings it all together, because now you have coordinate discovery with model discovery. And so that's the piece that we're pretty happy about. By the way, you can do much fancier things now that you have this architecture. So for those of you who are really interested in dynamical systems, you can directly learn, instead of a governing set of equations or parsimonious governing equations, you can learn something like embed it in a normal form. There's these canonical normal forms. So why not embed it in a normal form? This is work with Monocalia. What about learning deep conjugacy maps? So that's also with Jason Bramberger here. And you can learn boundary value problems in this architecture. So it's not just constrained to dynamical systems or PDEs. You can learn boundary value problems as well. And I'll end here, which is, I've just one more set of slides, which is the other piece of this architecture that we really like is what I think is a little bit more realistic for us to be doing. Everybody here, I made the observation, you're probably overeducated, you know a lot of math. This is why you're either professor or grad student or whatever you're doing and learning these things. So you have a great background. And isn't it disappointing to say, hey, tell the machine learning, you tell it to start from scratch, like as if it knows nothing. Most of the time, we actually know quite a bit of knowledge in the physics systems that we study. It's just that sometimes we're missing some physics. So this is work with Megan Ebers and Kari Koopman. What we are doing is say, okay, so instead of saying, just take what you don't know, just learn everything from just the data. Instead, we say, well, actually, I know quite a bit about my system. So instead of, I'm going to start with an imperfect model. In the imperfect model are things I know to be true. Like maybe I derive part of this model because I know there's conservation of mass. I know there's conservation of momentum. These are like fundamentals of the system. It's just that that model isn't giving me a good representation of the physics. I am missing some physics terms. So how do I do this? Well, it turns out this is actually pretty trivial to do within the SINDy architecture. If I know F, remember, I give you time series data X, so you can produce X dot, so you know the left side. Well, but if you know F of X, you just move it over there with it. So it's X dot minus F of X, and then you do a regression on a library of terms that would model the missing physics. So it's a trivial implementation. And the kind of places that you can start using this are things like the digital twin. And this becomes really important because the digital twin is sort of this technology architecture that is going to be pretty important for, I think, all of us in the future, which is I have a twin, right, a representation of the real physics system. And the problem with this, it kind of looks to your eye that they're kind of mostly doing the right thing. But if I'm trying to have this model as a accurate precision manufacturing representation of this, it's just not accurate enough. Because this model on the left is built with Platonic physics of model. Like it's a perfect model. Like here's a mass that's uniform and there's no sticking in the joints and there's no frictional forces. But the fact is this one on the right has frictional forces and it has sticking. And then someone comes and bumps it or oils the joints and now it's different. And so what you need to do is put sensors on this and learn the difference between your idealized model and reality. Learn a discrepancy model so this is an accurate model of the reality, and then I think you have a shot at making the digital twin work. And so with that, I think I'll kind of stop because mostly what I wanted to, like I said, show you is that within this architecture I presented to you, right, which is you take data, you're trying to learn and mapping to a variable set, and in that variable set dynamics, I've shown you at least two different ways to go with this. There's actually quite a bit of body of work that I haven't talked about, but I mostly wanted to kind of get to the concept piece, which is what machine learning is allowing us to do, especially this autoencoder with latent spec architecture. It's allowing us a framework. It's very general, which allows from data, I want to build a model, but I can specify the models, the kind of models I want out of that system. Do I want to try to learn a linear model? Do I want to try to learn a normal form, a nonlinear model? Do I want to just learn corrections to my model? It's up to you as a practitioner. The framework is very modular and you can basically have it do whatever you want. And so I just wanted to highlight that here through these set of examples. And with that, I'll go ahead and stop. Thank you so much for your time.
Thank you very much, Nathan, for that wonderful, fascinating talk and overview of so many different concepts as well. So it's time for questions. So in the audience, you have any questions, please, you can type them in the chat, or you can also raise your hand and we'll get to you. So maybe I can just start quickly with the question. So you showed how you can learn either a nonlinear model or a linear model and so on, and we can choose that. So when you say, for example, that you took the time series data and I mean, you can learn the different PDEs. What exactly is the output there? Is it the solution of the PDE itself, or like
No,
the
I'll show you exactly. So what it does when you do this, let's come back to the architecture here. Actually here. So what it's learning is essentially it's giving you, when you solve this AX equal to B, what it's going to give you is as many zeros. It's going to zero out as many library terms as possible and only give you the columns that matter. And these columns are associated with the physics. So for instance, here in the KDV, when I do this regression, UT, here are the two column elements that came out. There was this UUX term and UXXX term. This one had a coefficient of 6, this one of 1. All the other library terms got zeroed out. There was a diffusion, UXX in there, there was a UXXXX, there was a U squared. I mean, there's all kinds of terms in there, and these are the only two terms that came out of the library. So what I get out is the governing equation. And then I can say, well, does that governing equation make sense? I can now forward simulate it, see if it's the right kind of physics. Does it match up with my model? And so the output of the SINDy model is, out of all these candidates, here are the two terms that matter. And so, you know, here, that's what you're getting out of these terms here.
I see. And so, like, okay, so in the previous slide, then you had like various. Just wondering, like, how do you decide? Yeah. So, for example, you have 1 x, y, z, x squared, x, y, etc. So, how do you decide sort of where to stop? So, like, for example, in the KDV, how do you like, know which terms to consider, like UXX or UX squared and so on?
Yeah. So normally, what we have in the SINDy is we have an automated way to make this library. So for PDEs, what we typically do, if you look at most PDEs, the simplest thing to start with is we do something like, okay, go up to polynomials, either cubic or quintic, you know, like if you want more terms, you go up to quintic and you say n up to 4 derivatives. And so you look at all the combinatorial possibilities of that, right? So, and of course you can do beyond polynomials, but here's what's kind of interesting. Why do polynomials work so well? And this typically has to do with dominant balanced physics ideas. So if you look at our literature in physics, oftentimes, you know, the physics is very complex. When I throw a ball in the air, right, and if you were to catch it, and I say, I want you to write a model for the ball I threw through the air, and you would probably just say, okay, well, there's gravity, there's F equals ma, what was your launch angle and launch speed? But I say, well, wait a minute, why didn't you include quantum mechanics effects? Why didn't you include turbulent wakes that you were producing? Why didn't you include temperature effects? Partly because you go like, well, because they would have changed it like down to like, I don't know, how many digits way down there. It just doesn't matter. And so a lot of very complex physics, when you measure it, what's manifest is the dominant balance, which is often a Taylor series expansion of something much more complicated, which that's why most of our physics-based models seem to be polynomials with certain degrees and up to certain derivatives. So that's kind of what we went with. Like something like the Ginzburg Landau is so prevalent because it's sort of this very general, like Taylor series expansion. You just change the parameters and you get almost any pattern you want. And so that's kind of the philosophy here. Is you build a library, you can specify within the SINDy package, go up to quintic polynomials, up to 4 derivatives. And so it builds already, automates the building of that library, and then it will regress and see which 2 or 3 terms do I need to model your physics.
I see.
Yeah,
okay,
luckily we have all that built into the package, so you don't have to write it yourself.
I see.
Our grad students and postdocs have done a nice job with that.
I see. So thank you. Okay, so we have one question. Well, actually 2 questions. So Tapan Kumar is asking, thank you, Nathan. First question is, are these approaches working for time variant non-autonomous systems? And second question is, does SINDy is good enough to address traveling wave problems?
Yeah, so let's start with the easier one first. SINDy has no problem with traveling waves because unlike something like most model reduction techniques based upon a singular value decomposition first, where you do dimensionality reduction typically with FVD is terrible about handling traveling waves. But SINDy has no problem with it. SINDy handles that easily. Now, the more interesting one is the time varying problem. In other words, I have a PDE, and you know, if I go here to this picture here, it'd be like, suppose that the coefficient in front of that third order dispersion in front of this KDV was changing over time. Then when you do this regression, you have to have a coefficient that has a variable weight. So SINDy can be modified to that. In fact, Sam here, who's pictured, he wrote a parametric version of SINDy. And what he did is, you know, remember, we're kind of promoting sparsity. We're doing a sparse regression on this AX equal to B. And what he did is he did an algorithm that did group sparsity. So over time, all the time bins have to agree on the same PDE, but they can have different weights. And this then allows you to have a time varying coefficient. So you can modify SINDy to handle those parametric variations. All right.
Okay, so then I can just maybe read the question in case somebody is not looking at the chat. So Deepak Kumar is asking, can we produce a governing equation for a highly nonlinear system which should give the exact same output in terms of repeatability? Example, say additively manufactured components for heat transfer applications.
Give exact same output. Oh, so that's a good question. So I think your question is, so you're trying to almost reverse engineer, I think, which is to try to say, it's almost like a control problem, right? Which is you want an output to be stabilized from your governing equation, I think, right? We have not, if that's how I'm interpreting it correctly, we have sort of started looking at control paradigms to be integrated with SINDy. We have one paper on SINDy with control, which allows you to start thinking about this, but that one is actually a very open question. I think that one's actually an exciting one, is how do you bring in these model discovery paradigms when you also have a control in there, and that you want to sort of engineer. Here, remember I was saying, here's what I want out. So I want to set my regularizations to get what I want. You could also do the same thing with the idea of control, which is how do I set up regularizers so that I can actually set up the system to produce, I guess there would be repeatable outputs, right? So you probably could do something very interesting in that space. So Deepak, you should look at that. Sounds like a good thesis or a good project or a good paper.
Okay, thank you. So for the next question, maybe we can go to Niranjan, who has raised his hand. Could you please unmute and ask your question?
Yeah, hi, can you hear me?
Yeah, hi.
Yes, please go ahead.
Yeah, thank you, Professor Kutz, for a very interesting talk and very thought-provoking in the manner that you tied to these historical, the historical thread of how theories have been developed. So what I'm wondering about is in numerical methods, we talk about concepts such as convergence, stability, and consistency. So are there equivalent concepts when you're talking about deriving the model terms? So what I mean by that is, let's say you feed in this a series of images about these pendulum, and the neural network doesn't know that this is a pendulum. It just has these series of images, and it gives out these it gives out this model equation, which has the sine term, it has a linear term, and so on. If you give it a larger number of images or a smaller number of images, will it give out a sine square term or a sine cube term or a completely different model? So can we predict that this model that has been developed is actually it's dependent on the data to what extent, and to what extent will you get a completely different model which describes the data just as well?
Yeah, this is a great question, and I think it fundamentally gets to the heart of what we have to really be thinking about a lot these days as mathematicians in regard to machine learning and AI methods. The state of the art is simply, when I do this problem here, how do I know I'm right? How do I know I stabilize it? Like, the goal is, well, you know, I have enough data that I get a fairly robust solution, and how do I know it's a robust solution? I cross-validate it. So cross-validation is equivalent to a convergence study in this world, but it's interesting, it's very different. When you do a convergence study, typically you have some estimate, right, of if I take my delta x in half, my time step should be dropped by, you know, that's by the square or something. You have some estimates of what the convergence law should be. Here we don't have even an estimate of that. All we do is just like cross-validate, and if it holds up under cross-validation, we say it's good. And this is where, by the way, I think there's tremendous opportunity for the math world here. You know, when machine learning, I started working sort of in this space around 2007 and 8 is when I first started doing data methods. I didn't know it would blow up like this, right? I mean, I just started doing it because it was kind of interesting, and then it turned out that, like, oh, this is actually where the world has gone into data science and deep learning. But I think the people who have to get engaged, and in fact, my department and other departments, math departments, have been hesitant to get involved. Like, this isn't really math. This is what computer scientists do. But actually, I think the next big step is going to be the mathematicians coming in and saying, okay, let's clean this up a bit. Let's talk about convergence. Let's talk about error bounds. Let's talk about some kind of rigor on these approximation theorems that we need to pull together. And I actually think this next generation of mathematicians are going to have a massive impact on the field to take it away from sort of this art of cross-validation, like, oh, I cross-validated, so I'm just going to move on with my life, to actually there's something more principled to be done here for us to understand. So I'm pretty excited about this, but I actually do think this is the group of people that are going to do it. The computer scientists I don't think they're ever going to do it, right? They're going to be moving on to the next, right? They do other things than we do. They go off and, like, let's go build technologies. I don't really need, there's not as much pressure on them to really say why it works. They just have to make it work and then move to the next step. And this is partly why we even have conversations about ChatGPT and OpenAI. Are they getting ahead of themselves? Because they don't really take time to, like, self-reflect and figure out why it's working. They just, like, they're on to the next tool. And so great opportunities for all of our students. There's never been a better time to be coming into mathematics, ever, in the history of the entire world. This is the mathematician's moment. So I'm kind of on the old side, so I feel kind of, it's too bad, but, like, a lot of the young people have a whole career in front of them where I think they're going to see absolutely amazing things. So that's pretty exciting.
Excellent. Okay, thank you, Nathan. So, maybe we can go to the next question. So, Shayan says, thank you, Nathan, for the interesting talk. If we want to get a physics model, then is it better to know the number of independent variables? Like, for the example you gave for the pendulum, we need 2 variables. What if we have no idea of the number of independent variables?
Yeah, that's a great question. If I don't know the right number of variables, so if you look at the figure I have up here, the way we actually, if you didn't know it was a pendulum or the right variables, the way you do it is you take this latent space and you hyperparameter tune it. And you cross-validate. So hyperparameter tuning and cross-validation. So hyperparameter tuning means I don't know. Essentially, that's one way to say it. So whenever someone says they're hyperparameter tuning, it just means that they're just, I don't know what I'm doing, so I'll just try different things. So if you don't know what you're doing, you would just pinch this down. Okay, what if I use 4 nodes, 3 nodes, 2 nodes? Oh, 1, it still works. And then when I go to 1, it breaks. And so you go like, okay, I'll go back to 2. So somehow it seems like 2 is the right variables. So this is how we did it with all of our stuff. We just hyperparameter tune. And so if you didn't know the number of variables ahead of time, you would just hyperparameter tune that. You could always estimate the dimension by doing something like the SVD, get a rank truncation, roughly you know, if it looks like it's rank R, then you could start with R modes and make more than R, less than R, and see what works. That's what you do in practice. Train a lot of models.
Okay, so any other questions from the speakers? Okay, so Noor Mohammed has raised his hand. Please ask your question. Hello.
Nobody? Oh.
Okay, I'm not sure what happened there. Any other questions? Okay, so maybe I can abuse my position as a host and ask you one more question. So you mentioned the Kohl-Hopf transformation, right, for the viscous-Berger equation. In that case, you can either learn a linear model or a nonlinear model, right, depending on your coordinates. So, how is it determined? Like, in the sense that if you feed it the data, how do you know which? Because the terms are similar, right? You have a VT, you have a VXX, and in that case, you have a VT, and VX. So, how do you know which model it will actually output?
Yeah. So there's just two things. Well, we can do it in two ways. In one version, if we want to learn Bergers, we would do autoencoder, like say if we had spatial temporal data, we could do an autoencoder into a variable set where SINDy is enforced. So it just says, look, I want to learn a parsimonious representation is generically nonlinear, and it will do that. In the other version, where you learn a linear model, you force the latent space that when it goes through time step, it's a linear matrix multiply. So they're very one forces it to have a linear structure. And in fact, Craig Ginn, who I showed the results for the KS equation, that's actually where we started. We were like, can we just learn directly the Kohl-Hopf transform? And here's what's interesting. The neural network doesn't really care about your Kohl-Hopf. In fact, the neural network can find an infinite number of Kohl-Hopfs. So every time you train the neural network, it gives you a different linear transformation that works. There's an infinity of them, which is interesting by itself, right? So we don't understand that. But that's kind of interesting for us. And so that's what we did with that, and we can do some other things. But then if we just did SINDy forces it to be parsimonious, so then it learns one version of an equation, but has some nonlinearity in it. So anyway.
So has that
loss functions.
Okay, so if it finds like an infinite number of transformations, but has there been like a case where you sort of don't really know if there is a transformation or something like that, and then you try and then you don't know whether it's not able to learn or if that generally does not exist a transformation?
Yeah. The hardest one we did was just KS, right? We were just like, whoa, we got one. That was surprising to us that actually worked. And you know what? For us, that gave us hope. So I actually, in the history of linearizing transforms for PDEs, there's the Kohl-Hopf from 1950. Then you hit the early 70s, and you have the inverse scattering transform. So AKNS inverse scattering scheme, right, which applied to a class of complete integral PDEs, so like nonlinear Schrodinger KDV, right? So you have this transform in, you have the Marchenko transform back out. So beautiful theory, right, which worked for a restricted class of PDEs. It's been 50 years since that, and we still don't have any new linearizing transformations. So one of the exciting things to me about the neural network's capability to learn a linearizing transformation for the Kuramo to Shibashinsky is like, actually, I bet we could. I just feel, as my gut feeling, that we're missing something theoretically. I bet we can do it. I bet someone, maybe one of you on this call, will figure out how to actually do it, because the computer can do it. It did it. It showed us, it said, look, oh, you want something linear? I'll give you something linear. Seems that you're not quite smart enough to get it, but I gave you a hint. It can be done. So my hope is eventually that gives us, oh, we have a shot at doing some more linearizing transformations, and maybe this is the hope we need to sort of take that on to get our all the nonlinear PDE people out there to like, okay, this can be done. Let's go find it. It's been 50 years, so it's not like we should try to get something in this decade. So I think that's what I think. I'm too old, but the young people, they can take this on, right? So.
Okay, thank you very much. That is a fascinating thing that it can find such transformations. So there are a couple of hands raised. Satyajit, you have a question?
Yeah, thanks, Nathan, for answering so many questions and different types of things and introducing. So I don't know whether this question is very much related to today's topic, but I was wondering, let's say, because we are discussing about dynamical system. So I have a dynamical system which is unstable. So, and we know the stability depends on the parameters, right? So there is some critical parameters, etc. So I give a time series for the same system, let's say the Lorentz system, when it's stable. Okay, only the stable time series data, and I give also time series data which is unstable. So can your mod, SINDy, this architecture, or some other neural network architecture can predict the critical parameter for instability, like when it exactly happens?
That's a good question. I mean, the closest we've done to something like this is something like the normal form restriction. But I'm actually thinking that, look, this is a good place to try to build this in. Like, so the way I think of these neural nets a little bit too is you probably actually have some good ideas how you do this analytically, like to try to predict stability and instability of schemes. And I think the best way to make use of these neural nets is to say, take all the knowledge you have and you say, I know how this works. Let me teach this machine learning algorithm what I know. Here's the things I want it to know. And that is kind of what we have been doing, which is, hey, I know normal form theory and know how it's important. Let's just put it into this architecture and now force it to have my knowledge base. So imagine you could probably do something very interesting there where you could say, here's the kind of things I know about determining stability of a scheme and where it goes unstable or stable. I'm going to now come into my neural network architecture, put it in a loss function, the kind of things that I know are part of that system, and then start training and seeing if you can actually have a training data set that would allow it to now start understanding that and actually doing exactly what you're saying. It's probably very possible to do it. Okay. I actually don't think you have to do anything really fancy. I think you could just take your expertise, what you have a deep knowledge with, and just train that into the neural net. Say, look, take my expertise, but now give yourself more flexibility to work with problems that I can't quite work out with pen and paper, but really do the same thing I want. And it's a remarkable how well these things do there.
So one more related question. So, for example, if we look into Turing patterns, so if I let's say give the simulated patterns, it can classify whether it's labyrinth versus sparse versus other kind of things. So now going back to the model, whether because this various types of Turing pattern depends on the parameters, like what is the particular controlling parameter. So my question is also related something like that, whether the neural network will be able to predict, like if you vary this parameter, or if you move in the parameter space in such a way so you move from spot to strips or to labyrinth kind of thing. So that's the kind of things I am more curious to know.
Yeah, I don't know. I don't think I have a good answer to that, except for that sounds like a very interesting area to explore. Right? Morphing and patterns and Turing, mapping out instabilities, teaching a neural network all about Turing patterns, right? This is something you could probably embed inside of its architecture to start to learn these structures, and then you could make some pretty nice use of it, I bet.
Okay, thank you.
You bet.
Okay, so there was one more hand raised. Satish, do you have a question?
Sure. Hey, thank you, Nathan. That's a very nice seminar. And then a very non-mathematical question. So we do deal with the data. Like I'm a hydrologist, and then a little bit of climate. So I like to hear from you. Like when we go for these advanced techniques, do we need to see what kind of complexity does the data has? Or otherwise, data needs to have a complexity, then we go for these techniques. Otherwise, let's say like we don't know anything about the processes that tell about the data, or apply these techniques and then find out what is the complexity, and then if the complexity is too simple, and then go for the non-complex methods. Like this, I want to hear from you, please.
Yeah, it's a good question. A lot of times, what we always seem to start with is, if you're kind of interrogating a problem for the first time and looking at it, you really don't necessarily know too much about it. We always start with the simplest things possible, so we never do anything hard first. We always do the very simplest things first and build up and start to learn, and then we eventually get to the methods we need to actually apply it. So we rarely know what we're supposed to do ahead of time, but then by playing around with the problem, you start to learn, this is too simple of a method, it can't get to what I need. Make it, generalize it. Like for instance, for us, we almost always start with dynamic mode decomposition. You have spatial temporal data, just hit it with a dynamic mode decomposition, see if it works. If it works really well, stop. Don't make, you don't have to make your life harder for yourself. It's a simple linear regression. But if that doesn't work and there's more complex dynamics, then you start building on that platform to make it harder and harder as you go along. So, for us, it's mostly a matter of exploration ahead of time. We're trying to build algorithms that would do this, automate that for us, right? Algorithms that would start to do the exploration for us directly versus I got to go explore this, for a couple weeks. That we would run it through a battery of tests, and the computer would explore it and come back with a report in some sense.
Okay, thank you.
Yeah, you bet.
Okay, so there are two more questions which we can maybe take before we end. So Nur Muhammad has a question. Thank you, Nathan. If the parameter of the system itself is time dependent, okay. So for instance, the parameter sigma in Lorentz system is degrading. Sigma is following some degradation law. In such system, how can we approach for discovering the system?
Yeah, this goes back to an earlier comment I made, which is you can always do for this, if it's time-dependent coefficients, you would do a group sparsification trick. So you would say is I look at the data in chunks, and if I had some time-varying parameters, I would do a regression, and I would promote the same, they all have to agree on the same equation, but the coefficients can be different. So this is what Sam Rudy did to build parametric dependent models. So that's how you should definitely handle that if you have it.
Thank you. And the final question again from Deepak Kumar is, it would be great if you could point me towards some good references for a non-mathematician to kickstart the background of SINDy and its capabilities. Thanks for making the session interesting.
Yeah. Well, so this will be super, I hope you guys will forgive me, but maybe I can, this is a little self-serving maybe, but I don't, at least, but you asked, so I'll go ahead and just share this here. So I'm sharing my slides again, and so you should be able to see them here. So one of the things that we've done is if you go to databookuw.com, you have access to, you can download the PDF of this book for free. There's all kinds of videos, all the data, all the code is all there. And I have a bunch of books. Everything we've kind of made open source. You can watch lectures, you can download all the data, you can play around with code. And so that is a good place to start, because these textbooks are sort of written in a very whatever beginner fashion. So if you're interested in that, you can just go to these resources, download them, start playing with them, and you'll have access to everything. And like I said, all the PDFs